Hello everyone. In this video we will go over some examples of integrals in which you have to do simplification first, and if you don't do simplification it seems it's just something, the integral is something that you cannot find. Let us start with the first one. So when I look at this integral, I know how to integrate trig functions. I know when there's an x multiplied to sine, cosine, what to do. But when you have x added to cosine and it's squared, that's a little bit strange. However, this square is something that I can expand. So this is the first one square plus twice as first one times the second one plus a second one squared. And if you do this, then you see that, okay, my integral is really sums of easy integrals. Well, each one may need different things at different points, but anyhow, this is what we have now. It's much easier to handle. For example, the first one is what you find from the table. So this is this one plus 14. The second one, remember x time any polynomial times cosine x can be done by IBP, integration by parts. In this case specifically, we have u equals to x, dv is equal to cosine x, and you go from there, du is going to be dx, and v is going to be sine x. The derivative of sine x is cosine x. So this way I can apply IBP for the second one, which will be u vx sine x minus integral of v du, which will give me just sine x dx, plus. For the second integral, remember this is even powers of cosine and sine. For that you need to know how to apply that half angle formula to reduce the power. So here what I will do is use half 1 plus cosine 2x, half angle formula, yes. And this way we have now this part 14x sine x. Integral of sine x is negative cosine x. There's another sign there, so this will be 14 cosine x. This one, the second one will be half over 2x, and the last one is going to be half over 4 sine 2x, then plus c. So just by expanding, we turn the given integral into sums of three different integrals. For each one, we needed to use different techniques. Okay. The second one is even easier because when so you start like that, and you may say that, okay, I may need to do the trig substitution because I have something like x squared plus 3. But before you go in that direction, it's really necessary for you to work for or think for the simplification. So here, if I multiply this in, you notice that, oh my god, this is just simple. That's 2 half 5 over 2 plus 3x to the power half. And this is just power rule would do the job. So just needed to expand it, and then that will come out as you see. Okay. The last one here. Okay, so for the last one, I know that powers of sine, powers of cosine, and tan and secant, if I have all these things, this is good. Yes, I can do. But now I have tan over cosine. What does it mean even? Well, here what you can do is that you can write, well, first of all, Let me write this integral itself. Okay, I can either write this guy as tan cube x, then 1 over cosine cube, which is just secant to the power 3x. Or we can simply write sine and cosine, and what we will see is that there is a sine to the power 3x over cosine 6x dx. So I will go with different things here. So as you see, well, this one is an integral that we have worked with, and this one, if you look a little bit carefully, is a very good integral for substitution. It's again some different kind of trig integrals that you know how to handle. Let's just go on this two different ways or different methods and see what's happening. Here I have odd power of secant times odd power of tan. What I can do is that I can take out a power from each one of these guys. And now we know that tan times secant is derivative of secant, so we go ahead and use u substitution here, and what we do is that u is equal to secant x. As a result, well, du is tan times secant dx. So this way, basically, we have integral of this part is just du. That's good. This is u squared. And then remember that always we had this tricks that tan squared x is secant squared x minus 1. Yes, so that way then this last one is u squared minus 1. Yeah. So I have u squared minus 1 times u squared du, and that will give me just u to the power 4 minus u to the power 2 du, which is equal to integral. Oops, I can integrate that. I don't need to wait more, just this. But then I plug it in back. So secant to the power 5x over 5 minus secant to the power 3x over 3 plus. So that's how we can go with that in that direction. How about this other direction? Here, you see there is an odd power of sine up there. We know that the derivative of cosine is sine. So if I go and separate, so let me just go with the blue one again. So if I separate one power of sine, then everything else I can write it in terms of cosine. Why? Because the remaining power up there is even power of sine, and I can write sine squared is 1 minus cosine squared x. And when you get there, let me just do this one here. U substitution is what you need. So set u equals to cosine x, then the u is going to be minus sine x. Oh, if I said the derivative of cosine is sine, just multiple. For me, for the substitution, when you're going looking for the pattern, the multiple is not that important. So a constant multiple is not that important. So this part here then is du, this part is u to the power 6, and this is u squared. So my u integral is 1 minus u squared over u to the power 6 du. Let me multiply u in, negative sign in, so this will give me a negative u to the power negative 6 plus u to the power negative 4. And that is negative u to the power negative 5 over negative 5 plus u to the power negative 3 over negative 3 and then plus c. Okay, now I can go down and a little bit, write everything in terms of what we have. So this will be 1/5 of 1 over cosine x to the power 5 plus minus 1 over 3 1 over cosine 3x plus c. And if you look what we found before, these are basically the same thing, yes? Just 1 over cosine is secant, and you can turn it back to what we had originally there. Okay, so either way we get, but everything starts with this, one of these simplifications. So change this to the form that you want. And I have kept the very difficult one to the end. Well, this is very interesting integral, and I really suggest that you pause it here and think a little bit. If you have, it seems very simple, isn't it? Just 1 minus x, 1 plus x, and it's linear. There's just a square root there. What should I do there? Well, if you try a little bit, you will notice that none of the forms or none of the formats that we have or the tricks that we have will work here. But I know that when it comes to square root, I can handle the cases that is a square plus minus x square or x square plus minus a square. If you have that in mind, maybe that is something that you can use. Now, I can multiply both numerator and denominator by 1 minus x. Why do I do that? Because I want to generate what I can deal with, yes? Which is square root of, here it's 1 minus x squared. But what happens here is that we get 1 minus x in the numerator. Well, actually square root of this square, and then in the denominator we get 1 minus x squared dx. Oh, I know what to do with the denominator. In the numerator, if you look, this guy needs to be absolute value of 1 minus x. This must be this. I don't like absolute value in the integral, but if you note that since in the denominator I have 1 minus x squared, this means that x is either bigger than 1 or x is less than 1. Yes, less than it's x must be between 1 and negative 1. That is because I want to have x 1 minus x squared positive. So if x is less than 1 and bigger than negative 1, then your absolute value up there, you know what to do there. It's going to be positive. So this way, your integral is going to be 1 minus x. Absolute value is dropped now. But the key point is that now I know how to handle these cases. Okay. You can either now go with the trig substitution. This is at least what we started with, yes? So set x equal to be the sine theta, then dx is going to be cosine theta. Or, since now I changed it, I didn't have the plan for this, but I changed it. Now I can do some simplifications. And I see that, oh, this is now easier even than what we had in mind originally. Why? Because the first one is just a derivative of sine inverse, arc sine of x. Yes, and the second one, if you do the simple substitution, the derivative of the denominator, or u 1 minus x squared is equal to u, then you have minus 2x dx. Okay, so this way I can write negative 2x there and 2 there, and then my integral would turn into what? A half. Okay, I could put it in u du. And that's a simple integral, because I want to continue this and then plug in back in. Because this is derivative of just root u, and that means that we have 1 minus x squared there. Oh, this must be plus, yes. So we have sine inverse of x plus root 1 minus x squared plus c. So I challenge you to go in the other direction. That's an easy thing to do, but you will see that at the end you will come back, turn around, come back, and you will find what we found it here. Okay, so these were just examples of cases that you must start with some simplifications. So look for simplifications and see how this can give you a easier integral.